Hello everyone, I am Tanu Sharma and this is audio recording for visually impaired student from inorganic chemistry of chapter chemistry of actinides. Actinide constitute a series of elements following actinium. In seventh period of the periodic table, actinides belong to F block as these are formed by the gradual filling of F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides which follow lanthanum involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. This series of 14 elements is called actinides. Actinides along with lanthanides constitute complete F block elements. The ending "ide" in actinides is not appropriate because it more correctly means negative ions such as oxide or chloride. Actinides were named as a group of scientists. Actinions by group of scientists. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas radon as Xenon 54 6s2 4f14 5d10 6p6. After radon, the 7s and 7p orbitals gain stability relative to 5f orbital because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in 7s orbital, which mark the appearance of new elements francium Z87 and radium Z88 belonging to s block of elements. After addition of 2 electron in radon core, the 4f and 60 electron penetrate the s orbit 7s orbital. It is important to note that actinium, both the 5 and 60 subcell possesses almost similar energies. However, once filling start in f orbital, the f subshell becomes more and more stable, and the all incoming electrons start filling progressively in f orbitals. The general electron configuration of actinides can be signed as Rn 5f0 to 14 6d0 to 1 7s2. General characteristic of actinides electronic configuration. The actinides involve the gradual filling of 5f subshell. The electron configuration of the titled actinium Z89 is Rn61 7s2. Physical properties. Some of the physical properties of actinides are as melting and boiling point. The melting and boiling point of actinides are moderately high but are lower than those of transition elements. Density. Uh, the elements nearly uranium have very high densities. Americium resembles the corresponding lanthanide europium in being less dense than its neighbors. Ionic radii and actinide contraction. The size of the acetinide ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is poorly screened by the F electrons. And this steady decrease in ionic radii with the increase in atomic number is called actinide contraction. A comparison of M3 positive ionic radii of actinides with those of the lanthanides reveal that actinide and lanthanide ions are very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ions in case of actinides is shown. It is interesting to note that there is decrease in the atomic radii from thorium to uranium, which may be due to the increases in the most stable oxidation state from positive 4 to 6. In other words, the metallic bonding from thorium to uranium may be considered to consist of Mn positive ions with a total of n electrons per atoms. Oxidation state. The actinide elements show a greater range of oxidation state than the lanthanides, particularly in the early part of the series. Positive to oxidation state in case of actinides is very rare. Am2 positive has electronic configuration 5s7. It is analog to uh, Eu2 positive in the lanthanides but exists only in the solid state as the fluoride. AmF2 on the other hand, CF2 positive, US2, etc. exist as ions in solution. Positive through oxidation state is the most common oxidation state among all actinides. However, this is not always the most stable oxidation state in actinides. The first four elements, thorium, Pa, U, and Np, do not show positive 3 oxidation state as the most stable oxidation state. Thus, the most stable oxidation state of Th, P, and U are positive 4, positive 5, and positive 6, respectively. Although neptunium shows oxidation state positive 7 by involving all its valence electrons, it is not the most stable state. Positive 4 oxidation state is exhibited by all elements from thorium to Cf. The positive 4 oxidation state is exhibited by the elements from Pa to Am. The positive 6 oxidation state is exhibited by Lower actinides, one of the most commonly encountered compound of uranium in positive 6 oxidation state is uranyl nitrate dihydrate. It consists of a linear UO2 double positive ion surrounded by two NO3 negative ions and water molecules. The lower oxidation states are ionic, while the higher oxidation states are increasingly covalent. The positive 7 oxidation state is known only in oxocations of Np and Pu when alkaline solution are oxidized by O3. The important anions known in case of Np and Pu are NPO4 OH whole twice 3 negative and PuO6 3 negative. Color of anions. Actinide ions are mostly colored. The particular actinide ion depend upon the number of electron present in the 5f orbital. The color of actinide ion arises mainly due to a fifth transition. The color of characteristic cations formed by the actinide ions in aqueous solutions are given. In addition to FF transition in actinides, the color can also arise due to FT transition as well as charge transfer transitions. The color of the actinide ion solution because of FF transition occur in the visible and ultraviolet regions. We have already encountered this FF type of transitions in case of lanthanides as well. Since the 5F electron in case of actinides are projected out more in space than 4F electrons in lanthanides, these 5F electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterize easily. It has been experimentally found that the absorption due to FF transition in case of actinides are nearly 10 times stronger and 2 times broader than FF transition lanthanides. It has been observed that actinide ions in higher oxidation state display predominantly charged transfer spectra. Magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic moments with the number of unpaired electrons This is shown by where the magnetic moment are plotted against the number of unpaired electrons. Reactivity. The actinides are highly reactive. These react with hydrogen, dihydrogen and form non-stoichiometric hydrides with the formula MH2 or MH3. They react with hot water and tarnish in air, forming an oxide coating. The actinides reacts readily with HCl, but reaction with other acids is slower than expected. The metal are basic and do not react with sodium hydroxide. The actinides react directly with the halogen to form a variety of halides. The redox potentials for known the Me3 positive ion couples are about minus 1.9 volt. Thorium and uranium chemistry has been exploited in detail. Occurrence and isolation of actinides. All the elements beyond actinium introducible are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is heaviest naturally occurring element with an abundance of 2.4 ppm in Earth's crust. Uranium. Since uranium is most important of all actinides, its chemistry will be discussed in detail. Caronite K2O.2UO3.V2O5.3H2O. Extraction of uranium. As already mentioned, the main source of uranium is pitch blende. The details of the extraction of uranium involves the following steps. Concentration. The ore is crushed to a fine powder and is subjected to conventional gravity separation to remove the high lighter impurities. Roasting. The concentrated ore is roasted on the earth of reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic, and antimony. S plus O2 SO2 4S plus 3O2 2AS2O3 4SB plus 3O2 2SB2O3. Acid treatment. The roasted ore is treated with dilute H2SO4 in the presence of an oxidizing agent such as MnO2 or NaClO3. This treatment converts uranium to a soluble uranyl sulfate. UO2SO4. The roasted ore can also be converted to a solution of UO2 NO32 by dissolving the ore in nitric acid. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution urine sulfate precipitate it as ammonium uranyl carbonate. Conversion of uranium in uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with Charcoal ore with hydrogen U3O8 plus 2H2 gives to 3UO2 plus 2H2O. Production of uranium. Elemental uranium can be produced from uranium dioxide by using either of the two methods. U2 is heated with vapors of HF to form uranium fluoride, which in turn reacts with magnesium to yield uranium metal. 2 by converting U2 to a volatile uranium tetrachloride by heating it with elemental chlorine presence of charcoal. This is followed by reduction with elemental sodium. Chemistry of separation of neptunium, plutonium, and americium from uranium. The three elements that follow uranium in the acetinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the oldest known element amongst the actinides. Naturally occurring uranium contains two main isotopes, U92 238 and U92 235, which occurs in the ratio 99.3 and 0.7% respectively. Isotopes of plutonium Pu can also be prepared by N2N reaction, in which fast neutron is added with the subsequent loss of two neutrons without allowing time for the intermediate products to decay. The yields of the heavier elements is controlled by two factors: the half-lives of the various isotopes by their ability to absorb neutrons. The separation of these elements from uranium is extremely difficult and hazardous. It is because these elements, including the starting material, are not only highly radioactive but also give highly radioactive fusion products. Plutonium, especially, is extremely toxic. A dose as small as 10 raised to the power minus 6 gram may be fatal, while smaller doses are carcinogenic. The separation of NP, and DM from U are based on the following chemistry. Stability of oxidation states. A steady decrease in the stability of high oxidation state with the increase in the atomic number have been observed with the increase in atomic number. The order of stabilities of the major ions involved are Am3 positive is greater than Pu2 positive is greater than Mp3 positive and U4 positive. Separation of these elements from uranium from fission products and from one another can be achieved by adjusting the solution containing them to a suitable redox potential. Extraction into organic solvents. The MO22 positive ions from solution can be extracted into organic solvents. The M4 positive ions are extracted into tributyl phosphate in kerosene form 6 MHNO3 solutions, whereas M3 positive ions are extracted from 10 to 16 MHNO3. Precipitation reactions. Actinides in the positive 3 and positive 4 oxidation state can be precipitated as their fluorides or phosphates from acid solution. The higher oxidation states give either no precipitate or can be prevented from precipitation by complex formation with sulfate ions. Ion exchange methods. Ion exchange methods are commonly used in a separation for small amount of materials, as in separation of americium. The fuel rods are dissolved in 7 molar HNO3 and extracted with 30% tributyl phosphate in kerosene. As a result, nitrates of UO2 2 positive plus Pu4 positive are preferably extracted in tributyl phosphate, leaving the other actinides, namely NP and DM, along with other fission products in aqueous solution. Thus, Pu4 positive is reduced to Pu3 positive. UO2 positive species present in kerosene oil on treatment with 0.2 and HNO3 gives UO2. On other hand, aqueous solution of reduced pure solution on treatment with nitrous acid gets oxidized to Pu. Transuranic elements. Elements with an atomic number greater than 92 are called transuranic elements. Before the Second World War, elements thorium, protactinium, and uranium were located below hafnium. The newly discovered element should be positioned immediately to the right of tungsten below rhenium. The properties of the neptunium resembled more than uranium, rather the rhenium. It was discovery of neptunium followed by the subsequent synthesis of new elements that were responsible for the new series of elements called actinide series. All the transuranic elements are radioactive in nature and have short half-life period. Neptunium. Plutonic americium were known prior to their synthetic separation via nuclear reactions. However, these elements were later found to be present in trace quantities in uranium ores. Synthetic routes of transuranic elements. A neutron may be captured by the nucleus with the emission of gamma rays. The neutron increases the mass number of the nucleus by 1 in 10 some energy released as gamma radiation. Further neutron may be added in a similar way. The other hand, the other method involves the capture of small ions by heavy nucleus, synthesis of transuranic element. Preparation of neptunium. It was prepared by M.C. Millen and Abelson in 1948 Berkeley by bombarding uranium with uranium 92-232 with slow neutrons when uranium 92-239 was obtained. Preparation of plutonium. It was discovered by Seeberg and his co-workers during the beta decay of neptunium 239. Neptunium 9239 gives to plutonium 94-239 plus 1 electron. Preparation of americium. Americium was synthesized by bombarding uranium 92-238 with alpha particles. Preparation of curium. Curium was synthesized by bombarding plutonium 94-239 with alpha particles. Preparation of berkelium. Berkelium was synthesized by Seeberg and his co-workers by bombarding americium 241 with high speed alpha particles. Americium plus helium BK plus neutron. Preparation of californium. Californium was synthesized by bombarding curium 242 with alpha particles. Preparation of einsteinium. Einsteinium was synthesized by bombarding U-38 nucleus with accelerated nitrogen nuclei. Two isotopes of californium have been identified. Preparation of nobelium. Nobelium was synthesized by bombarding curium 246 with accelerated stripped carbon, that is C6 positive, Cm plus C612, NO plus 4 neutron. The later of heavier actinide elements. The elements of curium onward, namely curium, berkelium, californium, einsteinium, etc., are named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the most accessible isotopes are given in table. It is clear from the table that curium is available only in macroscopic quantities, whereas the later actinides above the atomic number 100 have been prepared only in minute quantities. In other words, later actinides are available in tracer amounts. It is interesting to note that actinides show close resemblance to lanthanides. However, the actinides can be easily separated from the lanthanides because the actinides readily form complexes. For example, the actinides react with concentrated HCl to form the corresponding chlorocomplexes. If both groups of ions are absorbed of the cation exchange column, the actinides can be elated more conveniently with concentrated HCl. After elating the actinides can be separated from each other by ion exchange using citrate solution to elute them. Actinides, actinides with atomic number 98 to 102, that is californium, nobelium, also display positive to oxidation state. Except for nobelium, positive to oxidation state is strongly reducing in nature. However, oxidation state of curium are found in the solid state in compounds. Elements beyond Judd equal 103. The actinide series is complete at LW. We have already learned that half-lives of later actinides beyond atomic number 100 decreases considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that half-life of the elements will decrease further as new elements are discovered. The half-life of an element with an atomic number 108 is expected to be very very short, about 10 raised to the power minus 4 and 10 raised to the minus 6s due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of elements beyond 108. A major controversy came to light over naming these elements. The choice of the name of the element belongs to the discoverer. In case of post-actinoids, three nuclear facilities are in competition for the synthesis of each of now newly discovered elements. The facilities are at Berkeley, Dubna, and Darmstadt. It is extremely difficult to identify a nuclear facility had the true claim. In some cases, names are shortened by removing the repetitive letter. For example, Bi plus Im can be written as Bm, or Trium can be written as in short form it Trium. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of the element is derived by combining together the roots in the order of digits, which makes up the atomic number followed by adding em in the end. 106 un equal 1 plus nil 0 plus hex 6 plus em unil hagium. Comparison of actinides and lanthanides. Both lanthanides and actinides constitute elements of Havelock, and these give the gradual feeling of half orbitals. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties, but also differ in many properties. Points of similarities. Both lanthanides and actinides involve the filling of half orbitals. To both the lanthanides and actinides display predominantly positive 3 oxidation state in the most of their compounds. Due to poor shielding of 4F and 5F electron, both lanthanides and actinides show gradual contraction in size of their atoms, with the increase in atomic number known as lanthanide and actinide contraction respectively. Elements of lanthanide and actinides with same number of unpaired electrons display similar absorption spectra due to FF transitions. Lanthanides and actinides are highly electropositive and very reactive. Nitrides, sulfates, and perchlorates of trivalent lanthanides and actinides are soluble in water. Hydroxide fluorides and carbonates of trivalent lanthanides and actinides are insoluble in water. Both lanthanides and actinides can be separated by ion exchange method. Point of difference. Property. Lanthanides, actinides, metal orbitals. It involves filling of 4f orbital, another involves filling of 5f orbital. Energy gap between f and d orbital, energy gap between f and 5d orbital, energy gap between 5f60 in actinide is small. Binding energy of 4f orbital are higher in lanthanide. Binding energy of 5f orbital are lower in actinides. Oxidation state. Most common oxidation state is 3. In addition to some lanthanides showing positive 2 and positive 4, the common oxidation state is positive 3 in addition to some actinides showing positive 2, positive 4, positive 5 and positive 6. Shielding effect. 4f electron exert greater shielding effect, 5 electron exert poor shielding effect. Ability to form oxocation. Lanthanide do not form oxocation, actin form oxocation in higher oxidation state like UO2 positive, etc. Color of ions. Most of lanthanide are colorless, most of actinides are colored. Example UE3 positive red, etc. Complex and stability. The tendency to form complexes is small. The tendency to form complexes is large. They do form complexes with bonding ligands. Radioactivity. All lanthanides except promethium are not radioactive. All actinides are radioactive. Coordination number. Lanthanides display coordination number 6, 7, 8, and 9. Actinides display higher coordination number 8, 9, and 12. Basic character. Compounds of lanthanides are less basic in character. Compounds of actinides are more basic in character. Thank you.